Welcome back, everybody. Learning as a hobby here. In this video, I'm going to go over my summary for section 1.3 in Niven, Zuckerman, and Montgomery, an introduction to the theory of numbers. Just as a reminder, I am going through the fifth edition. If you are want to follow along with the playlist, so let's jump into my notes here. Just bear with me while I bring them up. Okay, so this section of chapter one is on prime numbers. So we start with a definition of what a prime number is. Okay, so here's definition 1.5. An integer p greater than 1 is called a prime number or a prime in case there is no divisor d of p satisfying d strictly greater than 1, strictly less than p. If an integer a greater than 1 is not prime, then we call it a composite number. And then we jump right away into our first theorem for section 1.3, which is theorem 1.14. Every integer n greater than 1 can be expressed as a product of primes with perhaps only one factor, right? If it's prime itself, or if it's 1 or something. Actually, n has to be greater than 1, so if it's prime itself. Okay, so here's my proof. Let n be a natural number greater than 1. If n is prime, like we said, then n is a product of a single prime, right? It's just itself. If n is composite, then there are n1, n2 in the natural numbers with 1 strictly less than strictly less than n1, strictly less than n, and 1 strictly less than n2, strictly less than n, and n is the product of n1 and n2. And if n1, n2 are prime, then n is a product of primes. Otherwise, at least one of them are composite. Then, for example, N1 equals N3, N4, where N3 is between 1 and N1, and N4 is between 1 and N1. Um, by well ordering, this process must eventually stop, given that N1 is equal to a product of Nj, where j goes from 3 to k, where Nj is sorry, this should be strictly less than. Oh no, actually, sorry, the primes can be repeated. So actually, this can be less than or equal. All right, where the nj are strictly greater than 1, but less than or equal to j n sub j plus 1 for each j in the set from 3 to k. All right, then the nj must be prime. And a similar argument works for the factorization of n2. Therefore, n can be written as a product of primes. So it's basically like um, a consequence of well ordering. The fact that the process stops, right? Okay, since the primes in the factorization of n greater than 1 may not be all distinct, n can be written as a product of positive integer powers of primes. Then we have a note. This representation of n as a product of primes is called the canonical factoring of n into prime powers. However, the canonical factoring is unique up to the order of the factors. So you can have different orderings of the factors, but the factors themselves they're unique. All right, so here it looks like we have another little note. The canonical factoring of natural numbers into prime powers is unique up to order, which is what I just said. This is called the fundamental theorem of arithmetic and is proven later on in the chapter as theorem 116. In fact, Niven, the authors here do two different proofs of the fundamental theorem, and we'll see them in a few minutes. While it may seem obvious, it does require proof since there are number systems where unique factorization fails, and the authors give us two examples of such number systems. So, for example, consider the class epsilon of positive even integers. Note that epsilon is a multiplicative system. We'll look at multiplicative systems in Watkins. Actually, we're going to look at a stronger type of some stronger axioms on multiplicative systems than Niven is assuming here, because if you remember in Watkins, where all of the rings that we're looking at are commutative rings with identity. But anyway, basically what we mean by a multiplicative system here is the product of any two elements in the system is again in the system. All right. So take epsilon to be our universe of discourse. Then, for example, 8 is composite because 8 is a product of 2 times 4, and 2 and 4 are uh, elements of the the set epsilon, the multiplicative system epsilon. Um, but 10, notice, is prime since it's not a product of elements of epsilon, right? It's an even number. It's 2 times 5, but 5 is not an element of the set epsilon. And just as an example, the primes are for in this system are, for example, 2, 6, 10, 14, et cetera, et cetera. And now if you consider the number 60, 60 is an element of epsilon, but 60 has more than one prime factorization in epsilon. For example, 60 is 6 times 10. Notice that 6 and 10 are prime in the multiplicative system epsilon, but notice that 60 is also 2 times 30. And again, 2 and 30 are prime um, in the system. Therefore, unique factorization fails to hold in epsilon. So that's a kind of a simple example to, look at that's not where factorization is not unique. Then he gives us a more complicated example that is maybe a bit less artificial because this is the type of number systems that you look at in the branch of number theory called algebraic number theory, which is something that we'll look at later on down the line on the channel. And actually in Niven, I think chapter 10 is on sort of like an introduction to algebraic number theory. So we'll look at that in this book when we get there eventually. But anyway, let's look at this example. Excuse me. So a less artificial example, but rather more complicated, is obtained by considering the class, I guess we'll call it G. He uses this fancy symbol. I don't know if it's a C or a G, but I'm thinking it's supposed to look like a G for, Gaussian integers. Um, anyway, we look at the class G of numbers a plus b times square root minus 6, where a and b range over z. We say that this system is closed under under addition and multiplication, meaning that the sum and product of any two numbers in G is also in G. And by taking b equals 0, we note that z is a subset of the class G, right? There's a few things that we have to note before we show that unique factorization fails in this class. So first, we establish that there are primes in G and that every number in G can be factored into primes. So we need a definition here. The norm of a plus b times square root negative 6 in G is given by, it's basically just the square of the norm on the complex numbers. All right, so the norm of a plus b times square root minus 6 is the sum of the squares of the terms in the formal sum, right? So it's the norm of a plus b times square root 6 is the product of the conjugates, which is equal to a squared plus 6b squared. Right. Note that the norm of any number in that system is greater than 1 for all a plus b times square root minus 6, except in the class G, except for 0 and plus or minus 1, for which n of 0 is 0 and n of plus or minus 1 is 1. In fact, if b is not 0, then the norm of any number in that class is always greater than or equal to 6. Right. We say, and that's because, if b is not 0, then you get a squared plus 6 times b squared. And if a and b are greater than or equal to 1, then the number should be greater than or equal to 6, right? We say that we have a factoring of a plus b times square root minus 6 if we can write a plus b times square root minus 6 equals a product of, elements of the class, right? Where the norm is greater than 1 of both of the factors. The restriction on the norm is needed to rule out trivial factorizations like, 1 times a plus b root 6 or minus 1 times minus a times minus b root negative 6, right? And the fact that the norm of complex numbers uh, is equal to the product of the norms also carries over into this class G. So the norm of the product of elements in G is the product of the norms. So we just have to get a few of these like properties out before we can show the unique factorization fails. So that's what we're doing here. So from the norm of a plus b times square root minus 6 equals the product of the norms of the factors, it follows that 1 is less than the norm of x1 plus y1 times square root minus 6, less than the norm of the number itself. And same thing for the other factor, right? Which implies that any number will break up into only a finite number of factors since the norm of each factor is an integer. Right? A number having G as a number of G having norm greater than one, but that cannot be factored in the sense of 1.1. That's the way that we define factorization here, up here in 1.1, is called a prime in G. For example, 5 and 2 are prime in G since 5 and 2 cannot be factored into real numbers in G. Furthermore, if 5 is a product of a complex um, numbers with complex terms in them in G, then we get that the norm of the product of the norm of the factors is 25, and same thing for 2, we get the product of the norms of the factors is 4, but that contradicts 1.2. So 1.2 is where did I say that? Did I label it? It's referring to this fact here. Oh yeah, 1.2. It's referring to this fact here that the uh, the norms have to be greater than 1, or if b is not 0, greater than or equal to 6. Right? So that means that 5 and 2, for example, are prime in this class G. Now we're ready to show that unique factorization fails in G. Consider the number 10. 10 you can write as 5 times 2, and you can also write 10 as 2 plus square root negative 6 times 2 minus square root negative 6. So it has two different factorizations. And notice that we know that 5 and 2 are prime, but we don't need to even know whether 2 plus or minus radical negative 6 are prime in G in order to conclude that the factorization isn't unique. And just for your information, they are prime in G, but we don't actually have to know that the factorization is not unique. So that shows that the fundamental theorem of arithmetic doesn't hold in this class G. And then the authors say this is an example taken from algebraic number theory, which is a topic that we'll discuss. Oh, I said chapter 10, and I guess in chapter 9 is the chapter that we'll look at that. But like I said, there's algebraic number theory is a huge subject, so we'll actually look at some entire books that are on algebraic number theory in the future of the channel. All right, we get to theorem 1.15 here. If P divides AB, P being a prime, then P divides A or P divides B. More generally, if P divides any product of n integers, then P divides at least one factor AI in the product. So we do this by induction. So let P be A prime and P not divide A, then the GCF of AP is 1, and P divides B by theorem 110. Theorem 110 was one of the theorems that we had in chapter 1. So if you didn't see that video sorry, not in chapter 1, in section 1.1, 1.2. If you didn't see that video, you can look in the playlist. Next, assume that P divides the product A1 through AN, then P divides A1 or P divides A2 or P divides AN for any M between 1 and N for some natural number N. Consider the case where P divides the product of N plus 1 integers or positive integers. Then A1 through AN is equal to B, then P divides B times AN plus 1. So P divides B or P divides AN plus 1 by the base step. If P divides B, then P divides at least one of the factors A1 through AN by the induction hypothesis. Otherwise, P divides AN plus 1, and that proves the theorem. All right, so that was by induction on N. All right, theorem 1.16 is next, which is the fundamental theorem of arithmetic. Or if you want to think of it as unique factorization, then this theorem is on unique factorization in the integers. The factor, and what it says is the factoring of any integer n greater than 1 is into primes is unique apart from the order of the prime factors. Now, the authors actually give two different proofs of this in the book. So these proofs here are actually from the authors. These are not my proofs. I wanted to do the proofs from the authors because, like I said, they do it two different ways. So I'm assuming there's a reason why they want you to see two different methods of proving this theorem. I'm sure I'm going to show you both of them. So proof number 1 is this. Assume for the sake of contradiction that there is a natural number n. where n is greater than 1, such that n has two different prime factorizations. Then there are primes p1 through pr, q1 through qs, such that p1 through pr equals q1 through qs, where we have divided n by any common prime factors in its two distinct prime factorizations. Then theorem 1.15 implies p1 divides q1 or p divides q2, etc., etc. This contradicts that P1 is distinct from each of the Q sub Ks, therefore unique factorization holds. That's proof one. And then there's another proof of the same theorem. So proof two, and this one's a bit longer, but still interesting. Suppose that the theorem is false, so another proof by contradiction here. Then there's a least positive integer n that has at least two distinct prime factorizations. So for example, n has prime factorization p1 times, dot, 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 up to pr, and that's equal to q1 dot 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 up to qs, where the p's and the q's are all prime numbers that are distinct from each other. Not the p's are not necessarily distinct from each other, but the ones on the left-hand side are distinct from the ones on the right-hand side. Hopefully that makes sense. Um, Okay, so the PJs are all, like I said, are all distinct from the QKs, since if PJ were common to both factorizations, then n over PJ would be less, which is less than n, would have distinct prime factorizations, contradicting that n is the least such element. Next, without loss of generality, we can assume that P1 is less than Q1. Then we can construct the positive integer capital N, where capital N is defined as this product. It's Q1 minus P1 times Q2 up to QS, and we can actually distribute the Q2 through QS, giving us Q1 through QS minus P1 through times Q2 through QS, which we can replace Q1 through QS by P1 through PR, and the minus P1 through Q times Q2 through QS just comes along for the ride. Notice we can factor out a common factor of P1 from both of those. Then capital N obviously is less than N because Q1 minus P1 is um, less than Q1 through QS. And P1 obviously does not divide Q1 through, sorry, P1 does not divide Q1 minus P1. So we get two distinct factorizations of capital N, which is less than N, obviously, right? Which contradicts that N is the least such natural number with that property. Therefore, unique factorization holds for all N greater than 1. So two different proofs for the fundamental theorem. Okay, and then we have a bunch of properties and so on, and notation comments about notation here, which is written sort of just in sort of regular English. So I tried to break things down into a bunch of bullet points here. Hopefully, it's a little bit easier to wrap your head around all the statements that he makes here. He doesn't prove any of these; he just states them, and like I said, it's just some comments on some properties and some notation. So first, we'll start with this note in applications: the fundamental theorem of arithmetic. Sorry, in applications of the fundamental theorem of arithmetic, we often write an integer a greater than or equal to 1 in the form a equals. This is a product, like this um, the sigma notation, right? For summations, we have a similar type of notation for products, but we use a capital pi for that. So this is the product over all primes p of p raised to the alpha of p power, where alpha of p is a non-negative integer. And it's understood that alpha of p is 0 for sufficiently large primes p. If a is 1, then alpha of p is 0 for all primes p, and the product may be considered empty. Right, then we have some formulas here and we're labeling this 1.6 so we can refer back to it. If A is the product that I have written here, B is the product that I have written there, and C is the product I've written there, and A times B is equal to C, then the sum of the powers of the primes of the respective primes is equal to the powers gamma of P for C for all P by that follows from the fundamental theorem. Here A divides C, and we note that A alpha of P is less than or equal to gamma of P for all P. If conversely alpha of P is less than or equal to gamma of P for all P, then we may define an integer B, which is the product of the primes P raised to the beta of P power, where beta of P is defined to be gamma of P minus alpha of P, thus A times B equals C, which is to say A divides C. Thus, we see that the divisibility relation A divides C is equivalent to the family of inequalities alpha of P less than or equal to gamma of P. Right. Then we also have statement 1.7 here. As a consequence of the last bullet point, the GCF of AB can be written as this power of primes P raised to the minimum of alpha of P beta of P, where P ranges over all primes. And the least common multiple of A and B can be written like this as a product of primes P raised to the maximum of alpha of P beta of P, where P ranges over all the primes. Okay, the first part of theorem 1.13, which is the last theorem in section 1.2. Again, if you want to look back at my video for section 1.2, the first part of theorem 113 follows like many other similar identities from the fundamental theorem and 1.7, which is what we just talked about here. And also, since minimum alpha beta plus maximum alpha beta equals alpha plus beta for any alpha beta in R, the relations in 1.7 also provide a means of establishing the second part of theorem 1.13 as well. Okay, excuse me. Just another note here for calculational purposes, 1.7 should only be used when factorizations of A and B are already known, as the determining of the GCF of AB using the Euclidean algorithm requires less computation than the task of factoring A and B. Right? We call a square or a perfect, sorry, we call A square or a perfect square if A is n squared for some integer n. By the fundamental theorem, we see that A is a square if and only if all the exponents alpha of P and 1.6 are even. We say A is square free if 1 is the largest square dividing A. Thus, A is square free if and only if the exponents alpha of P take only the values 0 and 1. Finally, if P is prime, then P to the K divides A, but P to the K plus 1 does not divide A is equivalent to K equaling alpha of P. All right, so like I said, he writes this out in like a long paragraph, so I just wanted to bullet point all of the statements separately. All right, then we get to theorem 1.17, which is by Euclid. The number of primes is infinite. That is, there is no end to the sequence of primes, 2, 3, 5, 7, et cetera, et cetera. This is a very famous proof that I've seen this proved in many different ways over the course of my life. So I just used the proof from Niven for this because they're all kind of similar. Let P1 through PR be the first R primes, then construct the number capital N equals 1 plus P1 through PR, then N greater than 1. So N is prime itself, or N has a prime factor Q that is distinct from P1 through PR. Since P1 does not divide capital N all the way up to, PR does not divide capital N, right? Because you get a remainder of 1 whenever you divide by those primes. Since R was chosen arbitrarily for any R and N, this shows that the number of primes is greater than R, so the number of primes is infinite. Okay, then we get to theorem 118. There's arbitrarily large gaps in the series of primes. Stated otherwise, given any positive integer k, there exist k consecutive composite integers. This proof is relatively straightforward too. So all you have to do is consider the following sequence of numbers, n plus 1 factorial plus 2, all the way up to n plus 1 factorial plus n plus 1. Then notice that there are n numbers in the sequence, and each of them are composite because for any m between 2 and n plus 1, m divides n plus 1 factorial, and obviously m divides m, which means that m divides n plus 1 factorial plus m. Okay, let pi of x denote the function that outputs the number of primes less than or equal to x. Theorem 1.7 leads to a very weak lower bound for pi of x in that pi of x is greater than c times log of x. But the next theorem gives an inequality that is more suggestive of the true state of affairs. And this is the last theorem in this section. So this is theorem 1.19. For every real number y greater than or equal to 2, the sum of 1 over p, where p is less than or equal to y, is greater than log of y minus 1. And then there's just a note here. And I realized I put a red star next to this because I wanted to use this to prove theorem 1.19, but I just realized that I didn't do that. But I'll guide you through the idea behind it, and maybe you can write it up yourself. So since the sum of 1 over p diverges, theorem 119 leads to another proof of theorem 117. Theorem 117 was just to remind you. Whoops, I went past it here. Is this theorem by Euclid that there's an infinite number of primes. So since I didn't write it out here, maybe I'll just give you the idea. So if you look at this theorem 119, then if you notice, uh, log of y minus 1 uh, becomes infinite as y goes to infinity. And the summation 1 over p less than or equal to y, um, that sum then also goes to infinity as y goes to infinity. And if the number of primes were finite, then you would get a finite number for the sum. Since it diverges, that means that the number of primes has to be infinite. That's basically the idea. All right, but anyway, let's prove theorem 119. This proof is quite involved, and I don't think I would have been able to come up with this proof myself in a reasonable enough amount of time to make this video. So I'm taking the proof from Niven, Zuckerman, and Montgomery. So this is their proof of this. Let y be a real number, y greater than or equal to 2. Define capital N to be the set of all positive integers n that are composed entirely of primes p, not exceeding y. Since there are only finitely many p less than or equal to y in absolutely convergent series don't change values when the terms are rearranged, we see that, so we're labeling this as 1.8, the product of the geometric sums 1 plus 1 over p plus 1 over p squared, et cetera, for all primes p less than or equal to y is equal to the set of all natural numbers in the set capital N, where we're summing up, the reciprocals of those numbers. If n is a natural number and n is less than or equal to y, then n is an element of capital N, which implies that the sum above contains the sum of all n less than or equal to y, 1 over n. Let m denote the largest integer not exceeding y, then by the integral test. So before I actually show you this, you do have to understand a little bit about infinite series here. So hopefully you have at least studied infinite series up to the level of Calc 2. We haven't done that in Spivak yet, but we will eventually get around to it. But anyway, the integral test is a convergence test for infinite series. So by the integral test, we get this inequality here. So the sum n going from 1 to capital M of 1 over n is greater than or equal to the integral from 1 to capital M plus 1 dx over x, which is equal to log of capital M plus 1, which is obviously greater than log of y. Thus, the sum n of all the sum of 1 over n for all n in capital N is greater than log of y. Right. On the other hand, the factors on the left-hand side of 1.8 are geometric series, and if you know your Calc 2 stuff, then the sum of those geometric series sum to 1 minus 1 over p to the minus 1. So that means that the product of those geometric series is equal to the product of the 1 over 1, 1 minus 1 over p to the minus 1, where we take the products of all, where p is a prime over all the primes less than or equal to y. So I'm getting tongue-tied here, is greater than log of y. And then we have to use a lemma here, which he refers to as 1.9. So assume for the moment, we'll prove this in a second, but assume for the moment that for all v real numbers where v is between 0 and 1/2, e to the v plus v squared is greater than 1 minus v to the minus 1. Then take v equal to 1 over p. Then the product of all p less than or equal to y, we're taking the product of the exponent, the the exponential function evaluated at 1 over p plus 1 over p squared is greater than or equal to the product of 1 minus 1 over p to the minus 1, where p, we take the product over all p less than or equal to y. That's greater than log of y. Then by the property of the exponential function and properties of exponents, right? Then the product of the exponential functions evaluated at a sub I is equal to the exponential function evaluated at the sum of the a sub i's. That's just the sum rule for exponents, right? And the fact that the logarithm is monotonically increasing, we can take the logarithm of both sides to get sum p less than or equal to y, 1 over p, plus sum p less than or equal to y, 1 over p squared, is greater than log of y. Wait, we just took the logarithm of both sides of the formula up above here, or the inequality rather, up above. Then by the comparison test, we see that, again, the comparison test is a convergence test that you learn in Calc 2. We see that 0 less than sum p and p less than or equal to y, 1 over p squared, less than sum 1 over n squared, and going from 2 to infinity. That's a convergent p series, which you can see converges by the integral test. The sum n going from 1 to 2, from 2 to infinity of 1 over n squared is less than the improper integral 1 to infinity dx over x squared equals that, and that if you do that integral, you'll see that you get 1. Then log of y is less than the sum of p less than or equal to y of 1 over p plus 1, which implies that log of y minus 1 is less than the sum, and that shows the theorem. Okay, so like I said, kind of an involved proof, but hopefully all the pieces here make sense. Maybe I should make a note about this. This thing is equal to this because if you take the product of all things like this, and you multiply them all out, you get all the 1 over all the numbers that have primes less than y as factors, right? And then we have to prove that lemma that we talked about that we just assumed. So let's prove 1.9, and then that'll show that 119 is true. So define the function f of v to be equal to 1 minus v times the exponential function evaluated at v plus v squared. Then we need to show that if v is between 0 and 1/2, then f of v is greater than or equal to 1. So f of 0 is equal to 1, so that's okay. And then 2, take the derivative of f prime. Take the derivative of f. So f prime of v is equal to v times 1 minus 2v times x, the exponential function evaluated at v plus v squared. That's by the product rule and also by the chain rule. All right, notice that that's greater than or equal to 0 for all v in the interval from 0 to 1/2, which means that f is increasing on that interval. So that means that f of v is greater than or equal to f of 0, which remember is equal to 1 for all v in that interval. And that proves the lemma. So now we have everything that we need. So theorem 1.19 is valid. So this bound is good. Okay, just a few remaining comments to make here before we end the section. So here's a note. With more work, it can be showed that the sum p less than or equal to y, 1 over p minus log of y, is a bounded function of y for y greater than or equal to 2. And deeper still lies what's called the prime number theorem, which asserts that the limit as x goes to infinity of pi of x over x divided by log of x is equal to 1, which means that, well, just to define this, what we mean by asymptotic here, we say f of x is asymptotic to g of x, which we write as f of x and then the tilde sign g of x, if limit x goes to infinity of f of x over g of x is equal to 1, which means that the prime number theorem asserts that pi of x, which is the number of primes less than or equal to x, is asymptotic to x over log of x. That's called the prime number theorem. Now, they don't prove the prime number theorem in the book here, Introduction to Theory of Numbers, but it's one of the most important results in analytic number theory. And if you're curious, this is a book that we will be doing on the channel at some point. Let me just stop the screen share for a second. The one by Apostol. This is Introduction to Analytic Number Theory. And chapter 13 of this book is all about the proof of the prime number theorem. So eventually on the channel we'll get around to this, but if you want to check out the proof of the prime number theorem, chapter 13 is all about the proof of that theorem. Right. So let's just read the last thing here, and I'll end the video. So, like I said, the prime number theorem is one of the most important results of analytic number theory. And then I just said, see Apostol's book, Introduction to Analytic Number Theory, in chapter 13. Uh, and then they say, the authors here say it's not proven in this book that we're going through right now, but in chapter 8.1, a weaker estimate is established that goes in the direction of the prime number theorem. So that's section 1.3. Right. There is a lot of problems in the exercise set for section 1.3. So I'll try to get through those as quickly as I can, but it's probably going to take me a little while because, like I said, there's a lot of problems. And I think, let me take a look. I think there's like over 50 problems. Um, Looks like there's 53 problems, and a lot of them have stars next to them, which means that a lot of these are not going to be very particularly trivial problems. So it's probably going to take me a little while to do these. But like I said, I'll try to get that video out as soon as I can. And just a reminder, the PDF for my summary here will be up on the Patreon page if you want to download it as a PDF yourself. It just costs $3 a month to become a Patreon member of the channel. And then I got some other summaries for books, some other books that we're doing on the channel coming out within the next couple days as well. In particular, I'm going to try and get my summary for chapter 4 in Smith's book out next. So again, let me know what you guys think down below. Give me like and subscribe, and if you want to have any comments or questions, let me know down below, and I'll see you guys in the next one.